The ratio and the root test. The ratio test can be applied to any series. Since we are looking for the value of the limit of the ratio of successive terms in a series, and the conclusion reached by the ratio test rely on the idea of the absolute convergence and the theorem from the previous section. Assume the AK is not equal to 0 for all k. So then the ratio AK plus 1 over AK is defined. The theorem, the ratio test. Let the series AK be an infinite series and the R equals the limit of the ratio, the AK plus 1 and AK, as k approaches infinity. The idea is to compare the rate or the ratio of the next term and the previous term. If the R or the ratio is less than 1, the series converges absolutely. Therefore, it converges. If the R is greater than 1, including the R equals infinity, the series diverges. For R equals 1, the test is inconclusive. Examples. Use the ratio test to determine whether the following series converges. We have the series of k to the power 9 over 9 to the power k. For k equals 1 to infinity, then the ak term is k to the power 9 over 9 to the k, where k plus 1 or the k plus 1 term is k plus 1 to the power 9 over 9 to the k plus 1. We are looking for the value of the r, which is the limit value of ak plus 1 over ak as k approaches infinity. The ak is k plus 1 to the power 9 over 9k plus 1 divided by k is the same as multiplied by the reciprocal of the ak, or multiplied by 9 to the power k over k to the power 9. Simplify the expression as k plus 1 to the power 9 multiplied by 9 to the power k divided by 9 to the k plus 1 is the same as 9 to the k times 9 to the first, and then multiplied by k to the power 9. Cancel 9 to the power k and 9 to the power k. Take the limit as k approaches 9. We have 1 over 9 as the coefficient, and we are going to take the limit of k plus 1 to the power 9 divided by k to the power 9 as k approaches infinity. Since both numerator and denominator sharing the same real number power, so we rewrite it as k plus 1 over k, both of them raised to the power 9. As 9 the real number, so the group or the quantity k plus 1 over k approaching to the value k over k as k approaches infinity or approaching 1, then the limit is 1 over 9 multiplied by 1 or just 1 over 9, which is less than 1. If the r value is less than 1, then we can say the series converges. In this example, we have ak equals k to the power k divided by k factorial. Then the ak plus 1 or the k plus 1 term will be k plus 1 raised to the power k plus 1 divided by k plus 1 factorial. Use the ratio test by finding the limit value of the ak plus 1 over ak or the value r. The ak plus 1 is k plus 1 to the power k plus 1 divided by k plus 1 factorial and multiplied by the reciprocal of the ak, which is k factorial divided by k to the power k. Simplify the expression. The numerator using the exponent property as we can write this as k plus 1 to the power k multiplied by k plus 1 to the first power multiplied by k factorial. And the k plus 1 factorial is the same as k plus 1 multiplied by k factorial and multiplied by k to the power k. Note that, just a quick review, the 3 factorial is 1 times 2 times 3. 4 factorial is 1 times 2 times 3 times 4, which is the same as 3 factorial multiplied by 4. So then we can say k plus 1 factorial is k plus 1 multiplied by k factorial. Then back to the problem. K factorial can be reduced. K plus 1 and k plus 1 can be reduced. Now we have the limit k approaches infinity of k plus 1 to the power k over k to the power k. This problem is similar to the previous problem, but the power is the k is not the real number. It's not the fixed real number. So then we cannot apply the same property as before, but we can rewrite it as k plus 1 divided by k all raised to the power k. Simplify a little bit more to adjust into the form that we can find the limit value easier, which is 1 plus 1 over k to the power k. With this way, we can see the limit comes out to be e to the first power. As e to the first power is greater than 1, therefore this series diverges by the ratio test.